last section, we spoke about, we ended off with talking about neutralization reactions. We've done our hydrolysis bit. The last part of acids and bases is where we're going to look at things called a titration. I did introduce it. Titration. All right. Essentially, this is a neutralization reaction. It's neutralization. Okay. You can have partially done. I'm going to deal initially with the neutralization or titration where the one neutralizes the other. So what are we going to be doing? We are actually going to be putting an acid plus a base to form a salt plus H2O. This is what we're going to be doing. We're going to be adding the one to the other to get those products. Okay, remembering these are our reactants and products over here. Okie dokie. Let's first of all talk about how do we do a titration. What do we actually do? Well, in your notebooks you'll see a thing. It's like a tube. It's got a little tap over here and it comes to a little apex over there, and this is called a burette. Okay, and what you do is you fill this up with a liquid, and out of there you can drip small drops into a liquid. Okay, so we can have our liquid over here. This is our liquid, and what we do is we drip small little drops of something into something else. Okay, now let's define a few terms. First of all, let's say write definitions. Okay, first of all, a known concentration. We're going to be talking about things with a known concentration. Okay, a known concentration is called a standard solution. Okay, you pre-make it. Okay, how? Well, you can use an acid or you can use a base. You dissolve. What is a standard solution? Known concentration. In other words, the concentration is the number of moles per decimeter cubed. Therefore, you know exact moles and exact solutions. Therefore, you can create 0.25 moles per decimeter cubed. All that you're going to do is you're going to measure out an exact mass and convert to moles. If you are asked how to do, there are some questions, create a standard solution of 0.25 of something, what will you do? You know the concentration, 0.25 moles per decimeter cubed. Therefore, if it's half a decimeter cubed, you know exactly how many moles to do, because we say this, don't we? We go back to the formula. We say concentration is number of moles over the volume. So you measure this exact mass to give us N. Right? So if that's 0.25 over 1, you'd measure out the exact mass, and how do you work out? You remember, you're going to be using for this one, N is equal to mass over molar mass always. So you can make a standard solution of anything you like. Now, that's a standard solution. Okay? Very often, I just want to put this as part of this one, if you'll forgive me. A standard solution of, let us say, 0.25 moles per decimeter cubed, okay, is often called 0.25 M. M over here it's got a known molarity. Please note, molarity is an M. So if they talk about a solution of NaOH of 0.25 M, that means 0.25 moles per cubic decimeter. That's quite important. A lot of textbooks, and I've seen it actually in papers, where they use the M. It's the molarity. Or if they say with a molarity of 0.25, you know what that means. The next one is an end point and an indicator. Let's first look at indicators. All right? An indicator is a liquid that changes color at the end point of a titration. Wow, more terms that we've got to know. An indicator, you've seen them before. We've discussed them before in acids and bases in previous years. What do we do when we look at it is there are indicators that in an acidic environment are one color, and in a basic environment they change color. Colorless to pink, blue, orange, yellow, pink, purples, and the universal indicator goes in a whole sliding scale. The first ones that we did is we used litmus paper. Remember the pink and the blue ones? And they changed color. That is an indicator. It's a color change. So it's a color change thing. It's essentially, it's like a dye essentially, isn't it really? Changes color as things go. So that's that. The indicators there. We're going to get on what indicators we're going to use in a minute. Now the end point. As you are doing a titration, all right, you plot a graph that looks like this. I'm not going to get into detail of this right now, but you plot a graph and over here it does that. The middle of that line is called the, sorry, not the midpoint, I was thinking middle, it's called the end point. Okay? We're going to do more on these graphs and do some, but that would be in either first year or A-level stuff that we're going to be looking at. Suffice it for the moment to say, let us say that this one here is red and it goes to yellow at there. All right? That now, if I plot the pH along here, all right, I've got 0 over there, I've got 14 over here, and I've got 7 over there. This end point, in other words, it changes in an acidic area, all right? It changes over in an acidic area. Now, there are 3 indicators that you have to know. The 3 indicators that you have to know are going to be the following. Methyl orange, okay, number 1. Number 2, okay, is going to be bromothiamyl blue. Bromothiamyl blue over there. And the last one is the one nobody can spell, let alone say, phenolphthalein. Phenol, P-H-E-N-O-L. Phthalene is terrible, P-T-H-A-L-I-E-N. Phenolphthalein. Now, okay, I'm sure that you won't be marked down for the English. What we're saying is we're saying, right, those indicators, the methyl orange, you don't need to know the numbers. I'm just going to draw a pH scale 14 there, let's say, and 0 here, and let's call that 7. Okay. We'd use this over here like this one over here, and this one over here. I'm going to just basically summarize the whole chapter into this graph. I'm going to say that this is red to yellow. This is acidic. This here is going to be yellow to blue. A roundabout, neutral. This is the end points are down in those zones. Okay, this is in the basic zone. Therefore, the last one is colorless to pink. The question you will be asked is pretty much, you will do a titration, they will give you an example of a titration, and they will say, suggest a suitable indicator for use in this titration. The following is the way you remember it. It means that over here, this is a strong acid, and a weak base. Can you see the tips again? I'm going to use my green. Strong, weak. The acid is too strong, so it's going to generally leave it acidic. Sorry, let me just, come on. Just give me the eraser here. Strong plus that leaves me acidic. Correct? That's what we did with the hydrolysis of salts. We used the same method. We say here, whoops, let me just use the same colors as I have been. This is going to be strong acid and strong base. And remember from the salts thing, we said cancel, therefore it leaves us with a neutral, because this cancels. That leaves us with neutral. The last one is obviously the red, is going to be a strong base and a weak acid. Weak acid and a strong base. And what did we say? We say, let's look at our green here. Okay, strong and weak. It's going to leave us basic. So you'd want to choose an indicator if you're mixing a strong base and a weak acid, ethanoic acid and sodium hydroxide. You would need to know that your end points are going to be in the basic zone. Therefore, you would be using phenolphthalein, because I put them in the order that you need to know them. Methyl orange, bromothiamyl blue, and phenolphthalein, which is pink. That essentially is what you have to know from the theory point of view, the terminology and the indicators. And when you are dripping it in, all right, generally speaking, in most of the textbooks, they're going to be going to completion. So there's not going to be a pH left behind, all right? That is something I'm going to do at a slightly later stage, where we do a partial one and we end up with a piece of, or a pH left behind. How do we do titration calculations? So how do we do the calculations? Right? Always start with a balanced equation. Always. And let us say we have A moles of acid plus B moles of a base going to give us our salt plus H2O. What you come is at the end point. This formula is what you get. Number of moles of acid of the acid over number of moles of the base is equal to A over B, which is concentration of the acid times the volume of the acid over the concentration of the base times the volume of the base is equal to A over B. That formula there, all right, you don't really have to memorize, because it's on the formula sheet, generally speaking, given. For those of you who don't get it, therefore you have to memorize it. Right? There is another way of doing it. I'm going to do that way as further examples, advanced stuff, where we're actually going to use the mole ratio. The same way, it's the same thing applies, because you're looking at the end of the day for mole, to get the mole hole right, the balance correct. Let us look at an example. An example here, we say a 25 milliliter solution of 0.5 m NaOH, okay, is titrated, okay, into a 50 milliliter sample of HCl. Okay, what is the concentration? What is the concentration of the HCl? All right. Now, straight away, we say we start off with a balanced reaction. So we're going to say NaOH plus HCl is going to go to NaCl plus H2O, and it is balanced 1 is to 1 is to 1 is to 1. So 1 plus 1 goes to 1 plus 1. These are my double arrows, by the way, because I'm moving at a bit of a speed. Now, what's the next step? The next step is we're going to say to ourselves, okay, we now say, right, what are we given here? Let's see. We are given, remember this, we're given NaOH is 0.5 ml. And we are told that how much volume? This is the concentration of the base. The volume of the base is 25 milliliters. Okay, that's what we're given. All right, and that is added to something of the acid. So first of all, we say, all right then, the concentration, all right, 25 moles of the NaOH, okay, is added to 50 moles of that. So we've got NaOH. So how many moles? We said red. 25 mol, 0.5. Therefore, number of moles of the base must be equal to, right? Remember, concentration is equal to number of moles over volume. Therefore, number of moles is concentration times volume. The number of moles concentration times volume is going to be equal to, concentration was 0.5, if I'm right, 0.5 times 0.025, right, which is going to be equal to, hang on, let me just check, 0.5, switch on, 0.5 times 0.025 is equal to 1 over 80, 0.0125 moles, right? That's the first one. So now we know that 0.125 moles of the base was used. How many moles of acid did it neutralize? You say the ratio that it neutralized is 1 to 1. There they are. So therefore, how many moles of, I must have 0.125 moles of acid neutralized. Isn't that so? Because they reacted, 1 mole of this reacts with 1 mole of the acid. Therefore, 0.125 reacts with 0.125 of the acid. Thus, I can now start on my acid, and I can say, well, let's leave it in red, shall we? Just for the heck of it. Let's leave it in red. So therefore, the acid had 0.125 moles, and the volume of the acid was 50 mol, which is 0.05 decimeters cubed. Correct? 1, 2, 3. Therefore, the concentration of the acid was equal to 0.0125 divided by 0.05 N over V, which is going to give me 0.25 moles per decimeter cubed, or 0.25 m, like so. Okay. I could also have done this. That was the first way, using the actual relationships themselves. That works when it's not at the end point. Now, also I could have said A over B was equal to concentration of the acid, volume of the acid, over concentration of the base, volume of the base. Therefore, I would have said 1 over 1 is going to be equal to concentration of the acid times 0.05 was that, over 0.5 times 0.025. Therefore, I would have worked out that Ca was going to be 0.25 m. This is the second method, using the formula, right? The first one uses the actual mole ratios. The second one uses the formula. We are going to look at another one now. Right? I'm going to put up another one. Oh, no, it's suggest a suitable, all right, indicator. They've said, wait a bit, suggest a suitable indicator. What did we mix? We mixed NaOH, so we mixed a strong acid plus strong base. Therefore, we're going to end up in the neutral zone, which means I'm going to then suggest, right, which one? Bromothiamyl blue. Because I know that the end point is in the neutral zone. Okay, and what about the hydrolysis of the salt? Well, there won't be any, all right, because it is going to be a strong acid, strong base. Therefore, my salt is not going to undergo hydrolysis. It's not going to give us an OH minus or an H plus going anywhere. It's not going to be acidic or otherwise. My next question is this. Here's another example. An example is 10 milliliters of a standard solution of 3M H2SO4 are used to fully neutralize to fully neutralize 25 milliliters of NaOH. Okay, what is the question is, what is the concentration of the NaOH? Right, so we say, right, H2SO4 plus NaOH, and we go and we put, that goes to Na2SO4 minus 2 and plus 1 times 2 is plus 2, plus 2H2O, and it's a 2 NaOH. 1 mole plus 2 moles is going to go to 1 mole plus 2 moles, right? So therefore, this is also going to be strong and strong. Bromothiamyl blue and hydrolysis of the salt. Okay, my sodium sulfate isn't going to leave me with an acidic or a basic solution when it's in the water. So let us see. Let's write down. What are we given here? All right, given 3 moles. That is a concentration, 3 moles in every cubic decimeter. I am given here 25 milliliters of the stuff. And the volume over here, that's a volume, and this is a volume of the acid here, was 10 milliliters, which is 0.01 decimeters cubed. You can see I'm just going through the same motions, aren't I? Now, what's my next step? My next step is to say, right, A over B. And can you see that's A and that's B, isn't it? Just go back up here. Just show you. Go again. A is 1, A and B. So I can just use the formula here. Right, is equal to CA VA over CB VB. That must be a half, 1 over 2. Then I say that is 3 is the concentration. The volume is 0.01 divided by concentration of the base times 0.025. That must be equal to a half. How do we solve that if it's the bottom? You cross multiply. So we end up with, just going to go from here to here, therefore 2 times 3 times 0.01, okay, divided by 0.025 must be equal to concentration of the base, which is equal to 2.4 moles per cubic decimeter, or 2.4 m. Okay. You can go through that with me again if you wish, but all I've done is I've just applied the formula, very, very straightforward. All right. Please remember pH could be included in this. I will do some, but not as part of this section of the work. I'm going to do those as more advanced chemistry. All right, I think the last example here, auto-saving. The last example here is 35 centimeters cubed. This is worth actually taking down. 35 centimeters cubed of acid, H2X. We don't know what the X is, we don't really care. I'll explain why. It is a strong diprotic acid. They could tell you that as well. It doesn't matter. All right, is added. What matters is the diprotic. Is added to 35 milliliters, 35 centimeters cubed, my bad, 35 centimeters cubed of HCl with a known concentration of 0.1 m. 0.1 m. Kevin, just put an M properly. Like that. Okay, 0.1 m. This is now used. This solution is now used or titrated to neutralize NaOH of concentration equal to 0.15 moles per decimeter cubed completely. Okay, we use 50 centimeters cubed of the NaOH. Right. Now, the way to look at this is actually, you can see it's all a bit higgledy-piggledy, isn't it? The way to look at it is, let's go through the steps. What did we do first? We said, all right, this is my H2X acid. Let's put down, I know the volume of this is 35 centimeters cubed. And then I added to that, I added the HCl, and it was another volume equal to 35 centimeters cubed. And they told me the concentration here is 0.1 m, moles per cubic decimeter. All right. Then over here, the concentration of this, we don't know. Therefore, the number of moles of H2X is, we don't know. Can I work out number of moles of this one? Yes, I can. the number of moles is equal to C times V. You see what I'm doing? Watch. This is going to be 0.1 times 0.035, because remember, 35 centimeters cubed. We want to go meters cubed, decimeters cubed, centimeters cubed. We want to go up 1. Up means divide, cube means divide by 1,000. Therefore, number of moles is 3.5 times 10 to the minus 3 moles of H3O. Correct? We've got 3.5 10 to the minus 3 moles of H3O. Why? Because this is an H3O plus some Cl minuses floating around as well, when this HCl is put into there. So now I know the number of moles of that. Let's look at the next piece. The next piece is we took that solution, all right? We took these two over there and we added to it the NaOH. And in the NaOH, I had Na and OH minus. And they told me that the concentration of this is 0.15 mole decimeter cubed, and the volume of this is 50 centimeters cubed. Right? So can I work out number of moles? Yes, I can. It's CV, which is 0.15 times change, always change to decimeters cubed, 0.05 decimeters cubed, 0.05 is going to be 7.5 times 10 to the minus 3 moles of OH. Now, in the neutralization reactions, right, what are we saying? We are actually saying that the H3O is actually working with the OH minus to form H2O. No, I'm not doing it as an equilibrium calculation currently. I'm just saying that the acid, okay, it's doing its neutralizing, not neutralizing. The acid is neutralizing the base, or the base is neutralizing the acid to form water. Correct? Therefore, what had to happen here? Let's just think. How much base did I have? This was moles of OH minus. If it completely neutralized, therefore, it must be total moles of the acid must be equal to total moles of the base. Therefore, the total moles of the acid must be equal to 7.5 times 10 to the minus 3. Because I'm just going to go up here and just put it in here. Okay, in red, yes. Inside here we have 7.5 times 10 to the minus 3 moles of OH minus. Therefore, in here, I need 7.5 times 10 to the minus 3 moles of H3O, don't I? I need that to cancel. I'm sorry I've gone over time. Bear with me. I need it in 1-to-1, don't I? Therefore, I need 7.5 moles, the same number of moles of H3O, to cancel out the OH minus to form water, because it's 1-to-1. Therefore, let's go back up. But hang on, I've got over here, let me just use in green, I've already got, coming from there, 3.5 times 10 to the minus 3 moles of H3O coming from this route. Therefore, how many coming from there? Obviously, let's call this X. Don't need to, but bear with me. Therefore, I'm going to put it in green. Therefore, 3.5x, this is from the H2x, H2 big X, moles, right, plus my 3.5 times 10 to the minus 3 moles. Therefore, the number of moles, the additional moles, let's go back to that, the additional moles needed, X, is going to be 7.5 times 10 to the minus 3 minus 3.5 minus 3.5. Because I'm equal to, that is 4. I'm pretty sure that comes out to be 4 times 10 to the minus 3 moles more of the H3O needed. Okay, now you say, all right, last of all, therefore the number of moles of H3O, the number of moles of H3O that had to be in here, this number here is going to be 4 times 10 to the minus 3 moles. Must come from here. So the H3O in here must have been 4, I keep putting concentration, times 10 to the minus 3 moles. Let me not use concentration. Okay, the number of moles of H3O in there needed to be that. Right, that's straightforward. The last part is you say to yourself, okay, where's the balance reaction? You write it now. H2X plus H2O is going to be 2 of those, and it's going to be 2 H3O plus, you don't really bother about that. What am I saying? I'm saying 1 mole of this gives me 2 moles of the H3O. Therefore, okay, we'll just put it there, shall we? A little bit more up. So we say, right, therefore, now what do I know? I know that I need 1 mole of that to give me 2 moles of this. But they've already told me that. That's 4. 4 times 10 to the minus 3 moles. Therefore, I need 2 times 10 to the minus 3 moles of the acid, the diprotic, because it splits 1 to 2, like that. Therefore, the concentration is going to be number of moles, 2 times 10 to the minus 3 moles. The volume we said was 35, 0.035. My answer is 0.05714 m, or moles per decimeter cubed. And that brings us to the end of acids and bases. That is quite a long one. I apologize for going over so much. Maybe you could watch this one, or should watch this one in half-half, but I just hope that I was very clear on what to do there. Whenever you get mixtures, draw it. Draw out the little beakers and put in the different stuff. It's easier to work it out. We did it with the solubility product. My apologies for running over time. I'll just keep talking. Cheers. Have a great one. Bye.